Okay, hello once again, everybody, and welcome to the Center for Health Informatics virtual speaker series once again. Today we will be hearing from a recent graduate of the University of Copenhagen, who is also a close colleague of our previous presenter, Dr. Knudsen. Dr. Xiaoyi Wang received his PhD in computer science in June 2020 from the University of Copenhagen and earned his master's in science in media informatics from the University of Bremen, Germany. His research interests include visual analytics, information visualization, and human-computer interaction. In particular, his current focus is on how interactive visualizations can help users understand machine learning models. In this talk, Dr. Wang will showcase his work he did during his PhD to bridge the gaps between users' comprehension and statistical models through interactive data visualization. With that, I'll pass it on to Dr. Xiaoyi Wang to start the presentation.
Okay, thank you. Hello, everyone. First of all, thank you very much for providing me with this opportunity and attending this talk. I also want to give special thanks to Kathleen and Sun for making this talk happen. Today, I will be giving an overview of my PhD work to show how visualizations can help users understand the stats models. This is the agenda for my presentation. First, I will start by giving some motivation for this research, as well as some background material. Then I will introduce the overall research question drawn from the motivation. Then I will go through the 4 projects to answer the research question. Then I will discuss the reasons among the relations among the 4 projects. Finally, I will conclude this presentation by talking about the limitation and future work. Since this talk is aiming for general audience, I will skip some research details and mainly focus on the motivation of the work and the solutions. A stats model is the use of mathematical methods to describe a relationship between input and output variables. This type of model can help users review insights of the underlying data, such as discover the causality or correlation between variables, find patterns in the data, predict future trends, and so on. To gain insights, it is important to have a model with good performance. However, building a stats model is complex and requires essential expertise. Data scientists and mathematicians are the experts of statistical modeling, but they are not enough because a real-world problem is often domain-specific. We need domain experts to actively engage in model building process. They might be biologists, chemists, or sociologists. Sometimes they even have to build models by themselves, but they have limited knowledge and experience. They need our help, and they are the main focus of my current research. When building models, they often face 2 challenges. Users with insufficient knowledge may have difficulty in evaluating models and making decisions. Therefore, it is important to understand stats models. However, understanding is a broad term, which is not only about comprehension of statistical concepts and model working mechanisms, but also involves in understanding how to select features, refine models, evaluate models, and interpret model statistics, etc. The goal of my research is to bridge the gap between user comprehension and stats models by interactive data visualization. This also draws the overall research question of my PhD work. How can data visualizations help users understand the stats models? I conducted 4 studies to answer this research question. In particular, I used 2 visualization approaches to address the 2 challenges. The 2x2 theme matrix explains how I combine them together to explore the space of understanding models. The column names are the visualization approaches, and the row names stand for the 2 challenges. Each grid cell is a combination of 1 challenge and 1 visualization approach, which serves as a theme. Each theme is investigated by a research paper. Based on the theme matrix, this slide shows how each paper contributes to the overall research question. I will explain them in the following section. In general, I use the user-centered methods in my research to acquire initial needs, analyze, design, prototype, and evaluate the visualization design. In particular, empirical study is the main method for conducting effective design studies. I will go through the 4 projects in the next sections. At the very beginning, I started the first challenge to explore how visualizations can help users evaluate models. Model evaluation is an important part of the model building process, which requires a deep understanding of how to validate, refine models, and interpret model statistics. Holdout and cross-validation are the most frequently used methods for the evaluation. As you can see from the figure, the 2 methods have different implementations, but the common ground is that the evaluation can be divided into 2 stages. In the first stage, users use the training dataset to train several models, say 6 models. They refine and validate such models by tuning hyperparameters. Some models will be excluded due to the bad fit of the training data. And in the second stage, users use the test set to evaluate how well the models predict on unseen data. This stage only involves interpreting model outputs and evaluating model accuracy. The 2 projects together contribute to the whole evaluation process. Project 1 investigated how tweaking parameters can help users validate and refine linear models in the first stage. And Project 2 explored how navigating plots can enhance the understanding of the model statistics and evaluate the forecasting ability on unseen data. Now let us have a closer look at Project 1, Reglan as assisting novices in refining linear regression models. It was collaborated with my 2 supervisors, Luana McLeod and Casper Hornbeck. When building linear models, it is necessary to verify the following model assumptions: linearity, normality, homogeneity, and independence. If one or more assumptions are violated, the model robustness will be highly influenced. Typically, we use data transformation to fix the violations. Here is an example using 2-case ladder power for data transformation. Users need to tweak different combinations of lambda 1 and lambda 2 from the first row in the table to form a linear relation between transformed x and y. And the second row of the table shows that keeping y the same, which means lambda 1 equals 1, and alter the values of lambda 2 for x. And this figure shows an example of transforming a nonlinear relationship to a linear relationship. As you can see that here are the values for lambda 1 and lambda 2. The following R code describes one iteration of refining and validating a model candidate by tweaking the lambda 1 and lambda 2. As you can see, this is there are several steps. So first, users need to pick up a combination of lambda 1 and lambda 2. Then they check the statistics of the fitted model. And then they check the normality, check the constant variance. And then they generate plots to visually examine the assumptions. And finally, they try to find the potential outliers or high leverage points. And at the same time, they generate plots for outliers and high leverage points. And actually, we need to go several iterations until an optimal model is found. This requires users to repeatedly go back and forth to steer multiple models by either duplicating or modifying this piece of code, which can be time-consuming, tedious, and error-prone. It is difficult for novices and even troublesome for experienced users. And for the GUI-driven approach like SPSS also suffers similar problems. There are several studies using visualization to facilitate the linear model building process. However, their focus is mainly on feature selection. And it seems the validating assumptions and fixing violations are not well supported. by the current tools so far. Therefore, we presented Regline, a visual analytics tool, to facilitate the iterative process of model validation and refinement. It helps novice users to steer multiple models, to identify outliers, to validate model assumptions and accuracy, to fix violations by data transformations, and to visually compare different models. Now let me explain the design of a Regline. So Regline is organized into 3 parts: View A, View B, and View C. In View A, users can load the data set and specify the X and Y of the dependent indents and variables. And this is the transformation matrix. The x-axis stands for the x exponents. So the x-axis stands for the x exponents, so the value from this table, and the y-axis stands for the y exponents. Users can choose the combinations of lambda 1 and lambda 2 for transforming x and y. And each selection in the matrix will yield a transformed model and associated matrix in View B. As you can see in View B, each column represents a model, which is corresponded with a grid cell in the transformation matrix in View A. For example, when a mouse is over on a column, all related information is highlighted in dark blue, including the grid cell in the transformation matrix. View B allows users to perform confirmatory data analysis. We provide R-squared, RMSE, also the p-value of the coefficient, statistics of variance and normality. View C allows users to perform explanatory data analysis. They can visually examine violations and compare certain models. They can even modify models by clicking the button Modify. So after the click, we enter into this modification mode where only the current working model is enabled. And the color blue stands for the original model for reference, and the color green stands for the model which can be modified. Users can remove potential outliers, for example, this point, by clicking. The statistics in the column will automatically be updated after each change. Let's watch a video to understand how it works. Oh, sorry. Okay, yeah. Okay, so to evaluate Regline, we conducted a think-aloud study based on the following study setup. There are many interesting findings from the user study. I would like to highlight two of them. First, participants felt that they had the flexibility to try different transformations, which brought different insights into the data. Second, we found that participants do not validate model assumptions in their daily practice, but they did it when using Regline. One participant explained, I feel I need to check the assumptions because the visualization draws attention to them. I should not ignore them, especially when I saw the red cross icons in the bar chart. Now, let's move to project 2, which focused on the second stage of the evaluation. We used the time series models as the starting point to investigate how navigating plots helps people evaluate the forecasting ability of time series models. In the second stage of evaluation, users only need to compare model accuracy and compare predicted with actual values. Table and plots are the common approaches facilitating the two types of comparison. The drawback is that users need to merge tables and plots cognitively for the evaluation. The table will become more complex when k-fold cross-validation is applied, because the table needs to show not only the average accuracy metric, but also the accuracy of each fold. Users might be overwhelmed. A straightforward solution is to replace the table with multiple charts. Users need to decide the sequence of observing these charts by themselves. However, this solution does not create a clear structure of visual exploration process. The sequence chosen by users may not best possibly reveal the connections among the charts. Therefore, we proposed a method to construct a graph which connects these charts. Then users can navigate through a series of charts with the guidance of the graph. First, we performed an analysis of all the charts used in the second stage for time series models. 4 types of charts were summarized for evaluating models' forecasting ability. Assume that we got 3 model candidates from the first stage. And this figure shows the accuracy of these 3 models and their corresponding syntax from different perspectives. And 1A, 2A, etc. stand for the charts, and label with B stands for the grammar of each individual chart. If you look at grammar 1B, 2B, and 3B, the Y in the grammar can be replaced with any accuracy metrics. In this scenario, we assign MSE maze to the Y in the 3 grammar respectively. This grammar can yield 9 charts, and there are 10 charts in total if for A, this chart is included. Second, we need to connect the 10 charts based on the closeness of the grammar. The definition of closeness is the number of steps needed to transform from the syntax of one chart to another chart. For example, the only difference in grammar between those 2 charts is the cross-validation fold is encoded as saturation in the chart. Therefore, we only need 1 step to transform from MA to MAF. This figure shows the number of changes needed from one to another chart in grammar. And the furthest the changes is 5, but the lowest is the 0. And then we connect these charts based on the closeness showed in the previous slide. And the color of the arrows indicate whether the connected charts share the same grammar or not. For example, plots connected by pink arrows share the same grammar. And we use this structure to get the navigation. Based on the structured graph, we built a visual analytics system to allow users to navigate multiple charts in a structured way. The purpose of this tool is to help users better understand the relationship between accuracy, folds, and forecasts. Now let me explain how it works. So this view shows an enlarged chart in the graph structure. Instead of showing the whole graph for navigation, we only show an excerpt from the graph as a context menu. And the context, for example, the context menu shows all the neighbors of the enlarged chart in the graph. And users can navigate back and forth by clicking the many views in the context menu. We use animated translation to help users understand the connection between charts. Okay, let me further explain this setup. For example, this is the enlarged view, the view we are observing. When I want to transform to another view, I right-click to show the context menu. The context menu are 1B, 1C, and 3A and 3B, so connected, directly connected by this chart. For each individual observed chart, the context menu is different. If we are observing this chart, then the context menu consists of 2A and 3A. You may question why the graph structure is not shown as an overview in the system. The overview can assist users in orientation. Users can quickly switch between charts by interacting with the overview. But the quick switch can also distract users from exploring the connections between charts. And since the goal of this project is exploration, therefore we opt out this overview. So users can focus on exploration. Moreover, the graph is shallow. Navigating from the leftmost chart to the rightmost chart only needs 2 steps. It will not significantly affect the speed. If the graph becomes more complex, we might need the overview. Also, our user study shows that all participants did not feel lost without an overview map during the navigation. They felt the control of the navigation by the context menu. They can see different angles of the model accuracy by structured navigation. Now let's move to project 3. Models generate statistical results during the evaluation or prediction. Due to the nature of statistics, uncertainty is always an important part of the statistical results. For example, we use the model to predict when a bus will arrive in the next 60 minutes. As you can see in this figure, the prediction is not a definite time, but a probability distribution along the time axis. Therefore, a good understanding of uncertainty has a great influence on decision-making. Project 3 investigated how navigating plots can help users understand uncertainty and make informed decisions. Many studies use visualization to support different types of understanding uncertainty. For example, the arrow bar are made for estimating mean and its associated error, like standard deviation, confidence interval. The violin plot, quantile dot plot, and hops are designed for estimating probabilities. However, most of the work only focuses on using a single visual representation for understanding uncertainty at a time, which is not enough for the decision-making process. It is necessary to understand the several features of the uncertainty by observing different types of visualization. Therefore, we propose multi-state visualization to investigate how a combination of visual representations can facilitate the decision-making process. A multi-state visualization consists of multiple descriptive plots. Each plot is considered as a state, and each state is designed for a reasoning task. All states are shown through a shared plot, but only one state is displayed at any time through time multiplexing. States can switch between based on user input. And these are 3 types of plots support different estimation tasks. For example, the error bar chart supports estimating mean and error, and this one plot facilitates estimating data distribution, and those 3 plots facilitate estimating probability. To demonstrate the viability of multi-state visualization, we designed several multi-state visualizations by pairing these charts together. Let me show you some of the examples. Okay. Now let's move to project 4, which focused on specific domain experiment design in HCI research. Unlike project 3, understanding uncertainty, project 4 helps users make informed decisions about their experimental designs by understanding the relationship between power parameters. In research, scientists often need to plan an experiment to validate their hypothesis. The figure on the left shows the procedure of planning an experiment. They need to define different variables, units, sample size, and randomization. The figure on the right is an example of experimental design. Imagine we are working on a reading study. We want to test whether people using screen read faster than those using paper, and whether people using 2-column layout reading faster than those using 1-column layout. The independent variable are reading medium and layout. Each of them have 2 levels. For example, screen versus paper and 1 column versus 2 columns. We measure reading time as the dependent variable. Eventually, we want to test whether the effect size between 2 conditions is large enough to draw statistical conclusions. HCI sociology often involves human participants in the experiment, which is not easy to recruit. It's very expensive to because we need to allocate time to conduct the experiment and compensate participants with money or gifts. Since we are humans, we may feel tired if the experiment is too long, which introduces the fatigue effect of bias. Also, learning effects such as the practice effect or carryover effect also may influence the experiment if participants perform the same task multiple times. Therefore, we need to counterbalancing strategies to balance these effects out. To plan an experiment, we need to consider the following parameters. Determining sample size is a major challenge when involving human participants. An underestimated sample size can lead to missing effect, which is type 2 error. A priori power analysis can determine the sample size for the experiment based on parameter estimations. And these estimations can be added as the expected averages, potential confounds, counterbalancing strategies, number of replications, and number of participants. There is a dynamic relationship between those estimations and the statistical power. Changing one could possibly changing the other parameters. But the problem is that estimating these parameters and calculating the power are difficult. The current existing tools are neither intuitive or interactive. Therefore, we propose Argus, a visual analytics tool to facilitate the understanding of the relation between power and these parameters. Now let me explain the design of Argus. I think I need to switch to the tool. Okay, so this is the entry interface. In this interface, we specify the name of the dependent variable and the unit, also the range of that. To facilitate the interpretation, let me fill the numbers first, the value first. Yes, to facilitate the interpretation, we use verbal, use text to facilitate the interpretation. I will explain it in the next step. And the variability is that even if we do not consider the confounding effects, there's still some inevitable variabilities in the experiment. And here we specify 5. We can always go back to re-specify the numbers. Now I click simulate. Others is organized into 2 parts. On the left side, users can adjust the controls for simulating power parameters. On the right side, user can inspect the simulated results. So let's have a look at the input control first. In this expected average view, users can specify the estimation of the dependent variables in each condition by dragging bars. And with the confound parameters, the sliders, users specify the effect of the confound. So they can basically choose the estimations. And this is a preview to demonstrate how the changes will influence the average, the expected averages. And since people are different, they have different speed for reading, and we specify participant difference here. And in the experiment design view, user can choose how the experiment can be counterbalanced, and the number of replications and the number of participants. With the input controls, user can set parameters for the statistical results and power analysis on the right. In the pairwise comparison view, users can inspect how the results could looks like. And since this is a simulation, there are uncertainty existing in the simulation. We use animation to show the uncertainty, to represent uncertainty. And those, so people could interpret by the moving trends. If the mean and the confidence interval moving in this direction, that means screen is faster, vice versa. Basically, this view shows the difference between each pair of conditions at a mean and confidence interval. And this is the power trade-off view, shows the relationship between the number of participants on the horizontal axis and the static power on the vertical axis. And the power history view tracks the changes of the input parameters. So let me demonstrate how to use the tool. First, fresh tool first. Okay, I specify the information for the dependent variable. So basically, people could make the estimate those values either based on the literature or pilot study or their own hunches. So from my personal experience, I feel, well, using screen is faster than paper. So So I adjusted the time for paper to, for example, 42. And since I think 2 columns is faster than 1 column, so I increased the time for the reading time for 1 column a little bit. And similarly, I decreased the 2 columns for the paper. Then, as you can see, well, the simulator is working. So they calculate 30 simulations, and those stand for the uncertainty in the calculated results. And it seems our estimation is okay in the statistical result since screen is faster and two columns is faster. And this is trade-off view. The black dot indicates the current power. So now the default number of participants is 6. And with the current setting, we achieve a power which is around 0.3. Usually, we need the power above 0.8. So in order to increase the power, I might increase the participants. According to this chart, if I increase to 19 participants, no, not 19, 20 or 21 participants, well, I would possibly achieve the power. Therefore, I go to the experimental design view to adjust the number of participants to 21. Now, yeah, I have achieved a power above 0.8. And this is a history view. I can see each individual step in the past I did. But however, I have a very limited budget. That means I do not have enough time to conduct 21 experiments, and I do not have enough money to compensate participants. Then I consider about increasing the replications to reduce the number of participants. Therefore, I increase the number of replications to 2. The power is even better. Then I reduce the power to 17. Still, the power is good. And since I increase the number of replications, that means the experiment will be longer. And then it might result fatigue effect. Therefore, I specify the fatigue effect through this slider. Well, as to 2. So this indicates how this fatigue effect will influence the reading time in this preview. Since we have 2 replications and the user perform the same task many times, then they get familiar with the task. So we have learning effect in this case, and in this case I estimate the learning effect, for example, a carryover effect is 1, and similarly the practice effect I increase to 2. And also, since people are different, they might have different reading time, and I specify this difference in 4 minutes. Now, you can see that the power is above 0.8. And that means this setup could possibly most likely achieve the effect. Then this is a power history review. So if I want to compare 2 different setups, I use the mouse over on this dot. Then the orange lines will reflect the history operations. Okay, let me shift back to the presentation. Okay, in this section, I will discuss the relations between the 4 papers and the contributions. The targets of the 2 approaches are different. In particular, taking model parameters targets statistical methods, which requires users to take actions on methods. By contrast, navigating plots aims at the data, and it needs users to analyze the data. Furthermore, another difference between the 2 approaches is that taking parameters results in changing the models and producing new results dynamically, whereas navigating plots are based on the existing data and does not lead to any changes in the models or data. Our user studies suggest that the 2 approaches support the understanding of the models in different ways. It is highly possible to combine the 2 approaches for model development, since statistical methods and data are always intertwined. Tuning parameters offer users opportunities for creating a space of parameters where users can explore and compare alternative models and gain insights. However, the Project 1 and Project 2 explored the space of model parameters differently. Regline creates a closed search space for tuning parameters by enumerating all possible values. Users only need to find one from a list of options rather than come up with new combinations. This approach lowers the threshold for using the tool, and even people with little statistical knowledge can use Regline. By contrast, Argus offers users an open space to explore possible values of a model parameter. Users need to estimate the parameters based on their hunches, literature, or pilot study, which gives users more freedom to explore the space, but also raises the threshold and requires essential expertise to use the tool. The contrast informs that different design approaches are suitable for a specific situation and a target user group. And now I will talk about the limitation and future work. So the current design are only generalizable and scalable at a certain scale. For example, Regline only supports simple linear regression. It will be inconvenient when there are more than one independent variable. And the time series forecasting ability tool in Project 2 will become overwhelmed when seeing too many models. We need to fix these issues by careful designs in the future. Also, the first study is mainly focused on non-expert users. However, expert users may expect more advanced features and more flexibility to tweak parameters and navigating plots. Future studies should further explore how the two approaches can be useful for a more broad group of users. Finally, my current research mainly focused on the level of helping users achieve the best outcomes by tuning models, but it does not help us explain why the model arrived at a specific decision. We don't know whether the model is biased or not. This could lead to many social issues. As the future research, I would like to investigate how visualizations make models explainable and trustable. In conclusion, my PhD work investigated how data visualizations can help users understand the statistical models by tweaking model parameters and navigating plots. 4 empirical studies were conducted, and each study contributed to a specific aspect of the research question. Project 1 and 2 aimed to facilitate the model evaluation process. Project 3 and 4 focused on facilitating the decision-making process by improving the understanding of models. The 4 user studies suggest that our research have shed light on how the understanding of statistical models can be improved by tweaking parameters and navigating plots. That's it. Thank you very much for your attention. Questions, please.
Thank you, Dr. Wang, for providing some clarity around developing and evaluating statistical models through the lens of those two visualization approaches. I wanted to say congratulations on obtaining your PhD, and I think we can all very much appreciate the complexity of your research.
For more information on who we are and what we offer, visit our website at coming.ucalgary.ca/CHI. If you are interested in our services, collaborating with our team, or have any other inquiries, contact us via email at chi@ucalgary.ca.